The competitive inhibition equation has caused significant problems in the biological sciences. The use of this equation has obscured biological interactions, hindered understanding, and wasted nearly a century of research efforts. Here I will derive the competitive inhibition equation to reveal the problems associated with it. The only difference between the derivation I will be doing here and derivations found throughout the literature is that, rather than stopping with the production of the classical form of the inhibition term, I will rearrange this term, demonstrating that it represents an inversion of the inhibitor binding curve in this equation. Once we navigate through the problems associated with the competitive inhibition equation, I'll derive the straightforward equation that should have been used to describe changes in substrate affinity. Traditionally, the competitive inhibition rate equation is derived like the Michaelis-Menten equation by first defining the reaction catalyzed by the enzyme. So as enzymes are catalysts converting substrate to product, we can write a reaction scheme for this by first showing the enzyme and substrate coming together in a reversible way to form a complex. This enzyme-substrate complex is reversible, so we use the double-headed arrow to depict the process, where some of the complex will revert to substrate and enzyme. Alternatively, we will get the enzymatic conversion of substrate to product and will use the unidirectional arrow to show it is irreversible. This is the reaction scheme used to define the Michaelis-Menten equation, and for competitive inhibition, we are only going to add one more part, the formation of a reversible enzyme inhibitor complex that blocks substrate from getting to the enzyme. At this stage we encounter the first problem with the competitive inhibition equation, as this reaction scheme now presents a logical inconsistency based on the idea that the inhibitor completely blocks the substrate from interacting with the enzyme, but at the same time is expected to strictly affect only the substrate affinity. The substrate affinity for the enzyme can be viewed as a function of the points of interaction between the substrate and the enzyme. For example, if the enzyme-substrate complex is formed and stabilized by 5 interaction points, things that weaken or disrupt the interaction points reduce the stability of the complex, lowering substrate affinity. This reduction in substrate affinity is distinct from a blockage of the enzyme, which excludes the formation of an enzyme-substrate complex. However, in the reaction scheme for competitive inhibition, we can see right away that this inhibition that is only supposed to affect substrate affinity is based on the prevention of enzyme and substrate coming together. But let's move on for now, and follow the derivation of the competitive inhibition rate equation. So now we need to define some of the relationships we will use in the derivation. We will need an equation defining the rate of product formation. We will also need some equilibrium equations for the enzyme-substrate and enzyme inhibitor complexes, and a conservation of mass equation that will allow us to define the states the enzyme may be found in. For the rate of product formation, the rate is based on the concentration of the enzyme-substrate complex. So can be written as the rate V is equal to the rate constant, K cat, multiplied by the concentration of the enzyme-substrate complex. As for the equilibrium equation for substrate and enzyme coming together, we will define the equilibrium with the substrate affinity constant, known as the Km. In this equation, the Km is equal to the concentration of the enzyme, multiplied by the concentration of the substrate, divided by the concentration of the enzyme-substrate complex. The equilibrium equation for the inhibitor and the enzyme is essentially the same as the equilibrium relationship between the substrate and enzyme, except this time we will define the inhibitor affinity using the constant Ki. The Ki is equal to the concentration of the enzyme, multiplied by the concentration of the inhibitor, divided by the concentration of the enzyme inhibitor complex. As you can see, these equations only define the equilibriums for complex formation. They do not imply there is any quantifiable effect produced by the binding of substrate or inhibitor with the enzyme. In the case of the enzyme-substrate complex, we have already defined an equation for product formation, but here the effect of the enzyme inhibitor complex is not addressed. This could be due to the belief that a competitive inhibitor prevents substrate binding, so a term defining their effect on catalysis is not needed. But I want to stress the point here that the inhibitor equilibrium equation has nothing to do with changes in catalytic rate or the substrate affinity, and only represents the propensity for the inhibitor and enzyme to form a complex. Now, since the enzyme is a catalyst and is not consumed during product formation, the next step is to set up a conservation of mass equation, where the total enzyme concentration is composed of free enzyme, enzyme bound up in the enzyme-substrate complex, and enzyme that is blocked by inhibitor. Now that we have all the parts, we can start to put the rate equation together by defining the total enzyme in terms of the equilibrium terms that describe the enzyme-substrate and enzyme inhibitor complexes. This removes the terms for the concentration of the complexes. Once we do this, the next step is to factor out the term for free enzyme, from which we can then rearrange and solve for the free enzyme concentration. When measuring enzymatic reactions, we can control initial substrate and inhibitor concentrations, but we have no easy way of knowing the concentration of the free enzyme or complexes, so we want to get rid of these terms and define the equation based on things we can control or measure. So going back to our equilibrium equation for the enzyme-substrate complex, we will substitute this new term into the free enzyme spot. This new definition for the enzyme-substrate complex can now be inserted into the rate equation, and we are almost there. If we combine our rate with the term for the total enzyme concentration, we now have the rate that would be produced if all the enzymes were found in the enzyme-substrate complex, known as the Vmax, or maximum velocity of the catalytic rate. However, the bottom is still a bit of a mess, but we can multiply the terms together to clean it up and produce the classical competitive inhibition equation with the substrate affinity multiplied by the inhibitor term. This is where all derivations usually stop, and this equation is what can be found in the literature for the last century. But we're going to keep going to expose this inhibitor term for what it is, and show how wrong this equation is. So, focusing on the inhibition term, what is this? All association terms are usually defined with binding curves, and we saw that the inhibitor binding to the enzyme is defined by the same sort of equilibrium used to define the association between substrate and enzyme. But in the case of inhibitor here, we get 1 plus the inhibitor concentration divided by the inhibition constant. If we plot that we don't get a binding curve, we get a straight line. So let's see where the binding curve is hiding. First, let's multiply the 1 by Ki. This gives us Ki plus the inhibitor concentration divided by the Ki. Now we're going to do something a little odd and add 0 to the bottom, but in the form of inhibitor concentration minus inhibitor concentration. This doesn't change the equation at all, just makes it look more complex, and maybe we can start to see the similarity between this term and a binding curve. So now we have I plus Ki divided by I plus Ki minus I. Now we can divide the top and the bottom by I plus Ki, producing our binding curve for the inhibitor. But with this transformation, the problem with the competitive inhibition equation becomes obvious, as the term does not define the percent of the enzyme bound by inhibitor, but the inverse of the enzyme fraction free of the inhibitor. The equation thus shows that the affinity between enzyme and substrate is divided by the fraction of the uninhibited enzyme, which doesn't make sense. This is probably the reason that upon re-examination, experimental evidence for this sort of inhibition has never been observed. This has resulted in over a century of additional equation derivation to correct the problems introduced by the use of the classical inhibition term. Something, unfortunately, that could never be corrected without the recognition of its status as an inverted binding curve. Instead, what happened is the same methods used to derive the competitive inhibition equation were reused over and over again, producing the same flawed results. But this problem isn't even acknowledged by modern science, and theories like competitive inhibition are taken for granted as being correct. So much so that data related to inhibition studies isn't even questioned, just tabulated or presented as graphs in the supplementary data sections of research articles. But that can't be allowed to continue. So, in future videos we'll look at some of the published literature to see what we can pull out with WebPlot Digitizer and check how well the claims in some of these studies hold up. But first, as we can classify the competitive inhibition equation and classical inhibition terms as disasters that hobbled the development of the biological sciences, can we use the same classical approach to derive a rational equation that links changes in substrate affinity to the inhibitor binding equilibrium? Of course we can. First off, we must acknowledge that a change in substrate affinity does not stop the enzyme from making product. It just shifts the binding affinity from one value to another. So, in this case, the rate equation results from the enzyme-substrate complex and the enzyme-substrate inhibitor complex. We will once again define substrate affinity with the Km value, and we will now define the inhibitor affinity term as the dissociation constant for the inhibitor leaving the enzyme-substrate inhibitor complex. Now you could argue here that there may be a difference between whether the inhibitor binds to the enzyme before or after the substrate at this point, But it really doesn't matter, as a change in substrate affinity could result from either a decrease of enzyme-substrate association or an increase in the dissociation of the enzyme-substrate complex. Overall though, we are only really interested in what is the observable change in Km, which will be reflected in the change in the enzyme's catalytic rate. For the enzyme's conservation of mass equation, we have to expand it a little to include the enzyme inhibitor-substrate complex. And for simplicity here, we will also combine the free enzyme and enzyme inhibitor terms, as they do not play a role in the observable enzyme activity. From here we can start the derivation, but this time we will introduce the enzyme conservation of mass equation to the rate by multiplying the rate equation by 1. In this case, 1 is the total enzyme concentration divided by its components. For convenience, we will move the total enzyme concentration over with the reaction rate, and we are left with an equation that defines the rate based on the complexes, which we obviously can't know, so we now need to start inserting our equilibrium terms to redefine the equation in terms of inhibitor and substrate concentration. Eventually we get to an equation that has our hybrid free enzyme concentration in every term, so we can easily factor it out. And once factored in both the denominator and numerator, the enzyme concentration can be divided by itself, producing 1, effectively removing it from the equation. Now we have an equation where almost every term has the Km in it, except for the number 1 in the denominator, so we can easily isolate the Km value by multiplying everything by Km. This produces a much simpler equation where up top we can factor by the catalytic rate and the substrate affinity to produce the classical inhibition term. We can also do this on the bottom by factoring out the substrate term, also producing the inhibition term. From here we can divide everything by the inhibition term, getting back to the Michaelis-Menten equation, where the Km is now divided by the classic inhibition term. As above in the competitive inhibition equation, we are going to multiply the 1 by Ki. This gives us Ki plus the inhibitor concentration divided by the Ki. We then add 0 to the bottom in the form of the inhibitor concentration minus the inhibitor concentration, followed by dividing the top and the bottom by Ki plus Y, producing our binding curve for the inhibitor. In this case, it looks like the substrate affinity is subtracting itself based on the binding of the inhibitor, limiting the ability of this equation to only describe increases in substrate affinity or activators rather than inhibitors. But as I made a point of earlier in the video, the equilibrium constants used in the derivation of these equations have no bearing on how the inhibitor affects the substrate affinity. We can deal with this by introducing a modifier term, which will define the new substrate affinity produced by the binding of the inhibitor or activator. So there it is, a useful equation for defining changes in substrate affinity. You won't find it in textbooks and only rarely in the literature. So if you're a researcher, student, or know someone studying enzyme inhibition, stop using the competitive inhibition equation. And I don't mean you need to go back to searching the literature for suitable replacements, because in future videos, I'll be contrasting what's been proposed with logical simple solutions. So, stay tuned. Also, if you would like to submit some data for us to look at, I would also potentially be open to making some videos analyzing and comparing different inhibition models. Thanks for watching, like, subscribe, and consider supporting my work to see more of my content.